Okay, this is chapter 12 in ETRO143. So chapter 12 is about counter circuits, which are not combinatorial logic circuits. We will talk about two different kinds of counters. So although the chapter looks long, there are two different kinds of counters: ripple counters and synchronous counters. So here's my front slide, has fun things like counting chips, counting money, and at the bottom right is counting events. So you are going to do sequential circuits only in this chapter because things happen on a clock cycle. So the output state is changing every clock cycle or a certain period of time. So we'll have ripple counter with JK flip-flops, we'll have a frequency divider, and then we'll talk about synchronous counter. And then there is a couple of actually rather nice design examples in this chapter. So sequential logics, just to refresh your memory, are a mix of combinatorial logic gates and flip-flops, and we can use them to count events during a process. You can also use sequential circuits to control events in a sequential type event after event thing. So you can control events as well. So this is more about sequential circuits. The first thing that we're going to talk about is a counter, and we need a few definitions. So one of the definitions that we need is what is the modulus of a counter. So modulus, when we're talking about counters, means the number of binary states. So a counter that counts between 0 and 7 has 8 different states, and that's called a mod 8 counter. And then after it counts 0 to 7, which is 3 bits, right? 0, 0, 0 to 1, 1, 1. After it gets to 1, 1, 1, it starts over. So it rolls over and it keeps counting sequentially unless you do something to stop it. But so as not to confuse anybody, modulus actually has several meanings. So your book didn't mention that, but I think it's important to bring it up, especially in mathematics and programming. So in programming, modulus is an operator, usually written as a percent sign. So in programming, here it is down here as a, there I am. Here I am, is it written as a percent sign. In programming, if you were to say something like 12 divided by 5, using modulus, pause that for a second because I don't have the programming syntax correct. In programming, once again, you would write something like 12, and that literally means what is the remainder after you do 12 divided by 5. So 12 divided by 5 is 2 with a remainder of 2, and so the answer would be 2. So that's the programming definition, and that's how you would write it in a programming world. But I will also point out that you can have modular arithmetic, which has to do with a remainder again, and that's often used with clocks. So if you are saying something is 9 o'clock and you add 4 hours to it, 9 plus 4 would be 13, but that's 1 o'clock. So that's another modular arithmetic example. And then lastly, if you're talking about complex numbers, modulus also means the absolute value of a real or complex number. So be careful of the context. But in our counter circuits, modulus is defined as the number of binary states that the counter is capable of doing. And lastly, just to be funny, modulus also is a gastropod or a genus of small sea snails. So just to throw that in. Anyway. So these are sequential, and our counters are usually flip-flops, and they hold the binary state. So we said that our flip-flops were storage elements, and what we're going to do is put flip-flops in series with each other so that a 1 or a 0 kind of propagates through the flip-flops. But as a block diagram, this is just a block diagram of a counter here. I have a clock going in, and then these outputs, the 2 to the 0th place, 2 to the 1 place, and 2 to the 2 places, will just be incrementing with each clock cycle. So it will, the first clock cycle you'll output 0, 0, 0. Next clock cycle you would output 0, 0, 1. Next clock cycle 0, 1, 0, etc. So it will increment with each input clock pulse. The truth table looks as follows. It's just being driven off of a clock input, but you can see this is just counting in binary. And once you get to 7111, which is 7, or the 8th output, it rolls over and starts again at 0, 0, 0. So it doesn't count up and then count down, it continually counts up. This is what the timing diagram would look like. So the first clock cycle, my output cues would be 0, 0, 0. Nothing. Next clock cycle, the clock isn't showing here, but the clock would be going actually twice as fast at this point. If I can draw the clock in, there would be clock if you had a clock going. So maybe it's always on the rising edges is where I see the changes occurring. So at the rising edges, the output cues change, but you can see it's 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, and it's counting. And then I can write it in decimal here because I understand decimal better than I understand binary. So here is one example of how to, this isn't actually a counter, this is an example of how you would analyze a sequential circuit. This is a thinking exercise more than anything else, because after this little thinking exercise section of the book, we are going to jump right into counters that are packaged integrated circuits intended to be counters. So, but let's just look at how would you analyze a sequential circuit, because it's not the same as a combinatorial circuit. A combinatorial circuit, you'll write some Boolean expression for the output, but this one has a combination of both combinatorial logic and something that's a memory storage device. In this case, I have a D flip-flop with a clock edge. Yeah, so this symbol right here means that is an edge triggered clock rather than a level clock. So, and the symbol there means it's rising edge triggered. If I had a bubble drawn right here, it would be falling edge triggered, but the symbol, the little triangle on its side there, means rising edge triggered. So the way you analyze this circuit, I'm given a clock and I know it is rising edge triggered, so events happen on these pink spots, these rising edges. And I also see that I have a set and a reset that can override the clock signals. So if I reset this device, I don't care what the clock is going to do, Q will become 0. So good design practices, you turn on a circuit and before you start anything you reset your circuit. So the very first step in analyzing this circuit is what happens is make sure you have a reset first and start with a known condition, because a reset gives you a known condition to start with. I guess you could start with a set as well, but in this case we started with a reset. So step 1, a reset occurs. Reset is active low. See a bubble right here. Reset is active low. So at the very beginning of my timing traces, I have reset going low. The instant reset goes low, I don't care what clock is doing because these sets and resets override, but reset goes low here, and so Q, no matter what, will go low. So that's fine. And nothing else can happen. I can change my inputs D all I want, but nothing else is going to happen until a clock edge occurs. So so I have this other little input A going on, and A is low, but that's 0, and well, let's see, Q is low, so this is a 1. Q is low right now, so Q naught is a 1, and A is 0. I'm somewhere right here on the timing. A is a 0. This is a 1. 0 and 1 is 0. So D is a 0. Good. D is a 0. But I go along here, and at this point, I change. I think you can see my colored purple drawing in there. At this point, A goes to a 1. So the moment A goes to a 1, this value Q0 was still a 1. I have 1 and 1. 1 and 1 is 1. So D goes to a 1. Nice. But my Q's have not changed yet because a clock has not occurred. Now at this point, a clock occurs, and whatever the value of D is can now become Q, and that's what happens. So D is 1 at the clock edge, and so Q can now become 1. And so we can progress in this fashion, but like I said, this is really a thinking problem about watching what's going on and when it's going on and where the clocks are occurring, because in the absence of set or reset, changes occur at these clock edges. And at these clock edges, you look at what the current value of D is, and then Q will become it. So that's how you would analyze it. It's a little bit of a thinking problem that you should just sit and think through. There was another example in your book of using JK flip-flops instead. And again, it's a thinking problem. It is not really doing a counter application. So, and then it has the example and the answers are in your book too. So you can walk through that thinking process if you would like. Oops. So next I have, let's progress into making it actually be a counter. So we're going to talk about ripple counters. Ripple counters are going to be different than the second half of the chapter, which are going to be synchronous counters. I like the synchronous counters better, and you will see why when we get to it. But let's talk about what a ripple counter is. So we're going to form it with flip-flops, and we're going to cascade the output of one flip-flop to the input of the next flip-flop. So that's why it's called a ripple counter. If you want to make a 3-bit counter, it will take 3 flip-flops. And how many outputs will you have for this counter? You will have 2 to the 3rd power, which is 8 different combinations of output. Those will be 0, 0, 0 through 1, 1, 1, or 0 to the number 7, and that definitely corresponds, 0 to the number 7 corresponds to 8 outputs. So we say that the modulus of this counter is 8, or it's a mod 8 counter. So we are going to look at, going forward, a mod 8 counter, a mod 10 counter, and a mod 16 counter. So that's the terminology. Mod 8 means there's 8 possible different outputs, all in binary. So here's an example. I said it takes to do a mod 8 ripple counter, you need 3 flip-flops. So this is what happens. And I'll show you why it's also called a ripple counter. This is a clock pulse. Here's the bubble on the input. It's edge sensitive because I have this little triangle here. So it's falling edge triggered, or you could say negative edge triggered. Look, J and K are tied to 1. What does that mean? That means I'm in a toggle mode. When J and K are both tied to 1, I'm in toggle mode. And I'm not using set, so I've just tied set to a 1. And I have an option of using reset if I want, but I'm not showing that anything happens. So I start off on the first clock cycle. J is going to be I think the next slide has timing on it. So I'll just show you the setup. So you can see the Q is tied to the clock of the next one, and then this Q is tied to the clock of the next one. So changes that occur here cause a rippling effect down these flip-flops. And then the outputs are taken here. So this is the least significant bit, and this one will be the most significant bit. Let's show it on a timing diagram. So here's a timing diagram. So good practice initially, do a reset so you initialize all the flip-flop outputs to 0. Looking back on my schematic, I do a reset. All the Q outputs are now 0. And then my clock starts. And remember, my clock, whoops, sorry. Remember, my clock is negative edge triggered. So I'm going to look every time I have a falling edge of my clock. I am going to look at what's happening to the circuit, because that's where things occur, other than this reset initially that cleared everything and made my 3Q outputs be zeros. So that's fine and good. So I come here and I have a clock edge, and remember J and K are both set to 1, so I toggle. So the first output Q toggles. But look what happens when clock comes again. I'm going to toggle again because I've tied the first J and K's to 1 and 1. But so it's going to toggle and make that first Q go to 0, but that first Q going to 0 is going to trigger the second flip-flop, the second JK flip-flop to toggle. And so we have this cascading effect of every time the first flip-flop toggles, the second one gets a clock, and you can see there's a little bit of a delay before this occurs. So I'm toggled, falling edge, flip this one, falling edge, flip that. But that causes this one to flip. Falling edge flips first flip-flop, but that's a rising edge, so the second flip-flop doesn't change, and you have to wait to another falling edge, so I get a falling edge and triggering the second flip-flop, and that will cause then the input to the third flip-flop. So it's a ripple because the input clock is not connected to each flip-flop directly. So technically, this makes this an asynchronous circuit rather than a synchronous circuit. So it's a counter, and it's going from 0, 0, 0, next clock cycle 0, 0, 1, then 0, 1, 0, etc. So another way that we draw what's happening in a sequential circuit was with a diagram called a state diagram. So a state diagram shows all of the possible outputs and what output follows what in the sequential operation of this circuit. Every time there's an arrow, that means a clock pulse happened. And then you have this other event here that if reset not is a 0, you always start here. So anytime reset not is a 0, you go here. But if reset not is a 1 and there's a clock pulse, then you'll go here. Reset not is still a 1 and there's a clock pulse, and you go here. If I wanted to be just a little bit more thorough with this state diagram, there should actually be reset not 1 is a 0, and then, but if I have reset not is a 0, I go back to this state. It's another way of drawing it. So I could actually every time have reset, well, no, because it's asynchronous. I guess the way they have it is good. If it was synchronous, I'd have to tie it to a clock pulse. Okay, so these state diagrams are very useful in describing where a circuit goes and what its output is with each sequentially as it goes through each clock pulse. So I'm going to look a little bit closer at the output of that ripple counter because there are a couple of issues with it. So we have this reset. We start at 0, 0, 0. We're fine. And I'm still looking at a falling edge triggered series of 3 JK flip-flops. But there's a slight delay before this output happens. So let me go back to this slide. So clock is running, get a falling edge, this output changes, get a falling edge, output changes, but then after a little bit of a delay, this output will change. So this output changes after this output changes. There's a delay here, and this drawing here is showing that. So clock is running, the first JK flip-flop, there's a propagation delay. falling edge of the clock, propagation delay, output changes. And it comes over here. I have a falling edge of the clock, output toggles back. But the second flip-flop is depending on the output of that first flip-flop. So when this falling edge occurs, there's another propagation delay, and then the second flip-flop will toggle. So I have a propagation delay from falling edge on the first flip-flop, but since I'm dependent on the falling edge of the first flip-flop for the second flip-flop, that adds another propagation delay. And then you can see down here, for the third flip-flop, I add yet another propagation delay. So I have 3 propagation delays before this third flip-flop can flip its state. So that ultimately will make a limit, because if I had more and more outputs, eventually the last flip-flop, maybe there are 8 of them, the last flip-flop will slide more and more to the right because the delay will keep increasing. So that limits the maximum frequency that the circuit can do. Is limited by this propagation delay, and there's a little formula for it. So here's an example of how you would get a 16-bit ripple counter. So I said you need 2 to the n flip-flops you need n flip-flops to get 2 to the n outputs. This one has 16 possible outputs. So 16 equals 2 to the n, and if you solve for that, n equals 4, which is the number of flip-flops that you need to implement it. So here's just an example, and it will continue to count until you reset it. If you reset it, it will never get to 15. Like if I can choose always to reset at 10, and then I'm a mod 10 counter instead of a mod 16 counter if I always reset at 10, which I'm going to lead into here in a moment. So if you want for some reason to count down instead of count up, you just take the Q naught outputs instead of the Q outputs, and you'll get a counting down counter. And then we can do it in VHDL as you expected. The only reason I really put this in there's something different. You're counting on an intermediate state. Everything else that you've done before up to this point has an input and an output, but now we're using something that's a state in between some flip-flops to control the next flip-flops. So you have to change internally what's happening. So you create this thing called a buffer, and buffer is internal because it's not one of the inputs or outputs. So you have to declare a thing called a buffer. And buffers also generally mean storage. So if you put something in a buffer, you're storing it somewhere. So, so we declare this thing called a buffer because the output state is going to be stored. The other little thing that's different is how to create a negative clock edge. And there's some syntax here for creating a negative clock edge. They called the clock n_CP, which meant negative clock. And then n_RD meant a negative or a active low reset. So that was their choice of variable names. So it says if reset is 0, then Q gets 0. Fine, no problem. Else if, and then it says this unusual syntax, this clock event and clock is 0. So you want an event and it's going to 0. Then Q gets Q plus 1, or in other words, Q is incremented. So that's how you would implement the counter in VHDL. And of course you can simulate it and it just looks like a counter output. So, so let me point out something. Do I want to point it out on this one or the next one? I'm going to point it out on this chart first. So let's say I'm running at a frequency of the clock. Let's say the frequency of the clock is 100 kHz. So 100,000 pulses per second. This is the clock signal. And if I start to look at the output of this counter, this of course is 0, 0, 0, 0, and here you see 1, 0, 0, 0, 0, 1, 0, 0. So you can see it's counting, but the observation that I want you to make, and you might remember this from our very first simulations that we did, is what's happening with the frequency of these pulses on each of the individual lines, Q1, Q2, Q3. So here clock is running at 100K. What's Q0 running at? It's running half the speed. So this one is running at 50K. The next Q1 output is running again half the speed again. So I'm running at 25 kilohertz. And then this last one down here, the fourth one down, is running at half of this one again, so 12.5 kilohertz. So each Q output has the effect of dividing the frequency down. So that's how you can use counters to do frequency division. So a little note about the definition here. This would be a divide by 4 frequency divider. It's not that you're taking 100K. You don't take the clock and divide it by 4. You take the first output and, whoops, I have a line missing there, don't I? So you take the output, this is 50K, then it's 25K, then it's 12.5K, and then the last one, whatever that 12.5 divided by 2, 6.25. Oh, I ran off the edge. Okay, so yes, that's how you look. But actually, 50 divided by 4 is 12.5K. 50 divided by 8 is 6.25K. Well, anyway, you get all of those frequencies out if you want to, for some reason, have them. So this is what that next slide is illustrating, is that you can get frequencies that you're interested in from these this is a mod 8 counter. So I get a divide by 8 out of it. I think you get a divide by 16 out of it. It's sort of bugging me. But anyway, okay, so you can get those frequencies out. But there's a problem, right? You see that everything is a multiple of 2. What if you wanted to get divide by 5? I mean, I can do a divide by 2, I can do divide by 4, I can do divide by 8 in this example. But what if I wanted something in between, like divide by 5? How do I do that? So here's a divide by 5 example, and what you do is you start with the standard counter. So this is a mod 8 counter because it has 3 flip-flops in it. But you look for the state. What is a 5? 5 occurs when the output is 1, 0, 1. So if I look at what I'm doing in this logic right here, I'm saying when I get that state, so that means this guy is a 1, this guy is a 1, and then this one would be a 0 because I'm looking for the state 5, which is 1, 0, 1. When a 5 occurs, then 1 and 1 is 0. 1 and 1 is 1. It's an AND gate, so it's a 0. I reset the counters. So this makes my counter just go between 0 and briefly 5. So it's really going 0 to 4 completely, which is 5 states. Let me show you what happens. So first clock cycle I get 0, 0, 0. Second clock cycle I get 1. Third clock cycle I get 2. Fourth one I get 3. Fifth one I get 4. And then the moment I get the 1, 0, 1, which is the number 5, I reset. But there's a small delay that happens in the circuit. So for a very brief time, 5 shows before the reset puts everything back to 0, 0, 0. That's called a glitch. It's a glitch that occurs only on this line. It doesn't occur on any of the other lines. And I looked at your textbook, and it doesn't say anything about how to compensate for that glitch. But the way you compensate for it probably is, well, your textbook didn't tell you how. So a glitch occurs here in this ripple counter. Maybe the synchronous counters later on wouldn't have that glitch. That's probably it. So another thing you can do is you can do a manual reset. Like maybe you're doing a counter application and you want to manually reset it. So I think it's just nice kind of to see the manual reset. Here's a mod 6 counter, which means I start with a mod 8, I look for the number 6, and then reset with the number 6. So this is going to count 6 states. So when it hits the number 6, it will reset. But I can override it with this push button here. So if I do a push button here, I force a high on either one of these inputs to this NOR gate, will force the reset to occur. So here are the integrated circuits. We've looked at them now like by cascading flip-flops, but we don't really have to cascade flip-flops to make them. We can buy integrated circuits that are ripple counters. And your book mentions 6 different ones. There are some subtleties between them, but we'll go through some of them here. So the 7493 is a 4-bit binary ripple counter. So what would that be? That must be a mod 16. If it has 4 bits, it must be a mod 16. Internally, this is kind of interesting, and with the pinout here, what it has, you have 2 possibilities of resetting the circuit, and MR means master reset. You have the clock that's running. You have internal to the device, J and K are already set up in the toggle mode, and they let the different Q outputs come out. So you have our 4-bit outputs. But the other interesting little thing that they have going on here is that they have clock 1 going to the second flip-flop and clock 0 going to the first flip-flop. And you think, oh, what is that? So let me explain. So just running a signal right here, a clock right here, gives you a divide by 2 section, right? Because the clock runs and the first Q output is, the frequency is halved. So it's a divide by 2 section. And then there's this part right here that's a divide by 8 section. So a clock comes in, you get your first divide by 2, then it's divide by 4 at Q2, then it's divide by 8 right here. So what I need to do is connect this one somehow to the first flip-flop to the 3 flip-flops, and then I would get the divide by 16 total. So that's what we do. If we want to make it a divide by 16, in the previous slide, Q output went to this second flip-flop's input, clock input, but we have to manually tie that in. So the manual thing is shown here. If I wanted to make this a mod 12 counter, so it counts up to 12 and then resets. What is 12? 12 is 1100. Notice my order is different here, right? This is MSB. MSB is right here. LSB is over here, least significant bit. So 12 is 1100. That's most significant bit. That's least significant bit. So I have to look for the condition of 1100. So you look for the condition of Q2 and Q3 being 1s, and you send them over here to the master reset 1 and 2. So when you get 1 and 1 here, it resets, and I've made my modulo 12 counter, mod 12 counter. If, of course, you have to have this mod 16 connection in there as well. So that makes the mod 12 counter. So 7493 is a mod 16. It has a divide by 2 section and a divide by 8 section. The 7490 different device is a 4-bit ripple counter, but it's configured inside a little bit differently. It has a divide by 2 section and a divide by 5 section. It's 4 bits, but it's not going to 16 different states. It has 10 different output states. So this is useful as a decade counter. Decade means 10, and it's also useful for BCD applications. So they even noted it was commonly used in decimal display applications, or in other words, like our 7-segment displays, and we want to count 0 to 9, and we want to have 10 different output states. So we could be using this counter and driving our little 7-segment display to count between 0 and 9. I think that's what you're going to do in the lab, actually. And then there's a 7492, which is also a 4-bit ripple counter, but internally it's divided up differently. It has a divide by 2 and a divide by 6 section, which makes it form a mod 12 device. Mod 12 devices are often used for such applications as digital clocks. Why? Because there's 12 hours on a digital clock. So this one was the 7490. The 7490 is the one with the, look, I already forgot. I just read it. I'm not good at remembering the part numbers. 7490 is a mod 10. So it has divide by 2 and divide by 5 sections. So the first section has to have a divide by 2 and a divide by 5 section. So this would be the divide by 2 section right here, and this is the divide by 5 section right here. And then the 7492, this one was the mod 12. I think it was the mod 12 device. Yep. So let's look at at least one. Actually, I'm going to look at the first design application and the third design application. The second one is very much like the first. So it says we are going to have an LED turn on for 1 second every 13 seconds. This is a perfect application for a counter. Number 2 is very similar. Design example application number 3 is do a decimal counter to count between 000 and 999. So let's look at the first one. Before I look at the first one, I'm going to go and show you one thing about chapter 11, because we kind of skipped chapter 11, but there is an important device in chapter 11 towards the end of it that we need to look at. And this device is called a Schmitt trigger, or Schmitt inverter. So here it is, the symbol for it. It looks like an inverter, only it's got that little Schmitt signal in it. That's also actually called a hysteresis curve, just for the fun of it. This thing here is called, that little symbol is representative of a thing called a hysteresis curve, because the Schmitt trigger has hysteresis. And let me show you what it means. That when the output state changes, let's say we have voltage here, and when I get to 2.3 volts, for example, I can go, in this case, to a low, but, well, I'm not going to, hang on a minute, I got to go back and look at that, but let me show you how it works. So I have an ugly signal right here that I want to make a digital signal. I want to clean it up. So my ugly signal is rising up to a high voltage, a logic 1, and then it's coming back down, and it's pretty ugly. And if I just ran that through an ordinary inverter, I would say, oh, I'm above my threshold, make it a, this is an inverter, right, make it a 0. And then when I get back above the threshold right there, make it a 0, get below the threshold, make it a 1, and you get this kind of choppy, I didn't switch very well between 1 and 0. And the same thing can happen on the other side. But the Schmitt trigger, because it has hysteresis, will not switch quickly back to the opposing state, and that's what hysteresis is. So my voltage comes up and I get to a level to make a 1. I got to the level to make a 1, or it's an inverter to make a 0, and I go to a 0, but even though I have this noisy signal that flops back around these thresholds, the Schmidt trigger can't respond to it right away, and it misses the messy time, and it stays where it's at. Now there are some time limits involved here, but what you end up getting is that I passed the threshold, I switched to my output, and because this stuff happened really quickly here, I don't switch back and forth. And the same thing can happen on the negative side. So the Schmidt inverter is very nice for cleaning up signals without getting messiness right here that you would normally get from an inverter. So that was probably the biggest thing to take away from chapter 11, was using Schmidt logic to clean up messy switching or noisy signals. So back to our design example, we want an LED at some point to be off for 12 seconds, and then turn on for 1 second, 1 second, and then repeat. And we want to control this timing very, very precisely. Therefore, we are going to use a counter application. Now, you guys in ETRO122 will see this just fine, but I have a transformer here. So my transformer takes my 120 volts AC coming at the wall, out of the wall, which is running at 60 hertz, and it steps it down to a smaller voltage. So in this case, it stepped it down from 120 volts RMS to 12.6 volts RMS. And then I have a diode resistor here to limit current. The next thing that you see here is a thing called a Zener diode. And what the Zener diode does is it will conduct if the voltage exceeds a certain value, it will conduct. And when it conducts, it makes the voltage at this node be clamped to a certain value. So let me show again. A little mess up there, so it might be a discontinuity moment in the video. Let me show you the output of this Zener diode right here. So we've stepped down transformer is now at 12.6 volts. The way a Zener diode works is that if you exceed the certain voltage at this node right here, it's going to clamp it to a certain voltage. So I have 60 hertz signal running right now. This is going to be my 60 hertz signal, sine wave, time, and it's going up to well, it's 12.6 volts. It's really RMS, but for the sake of argument, I'll just make it say that it's going up here to 12 volts. And so what this Zener does is the moment it exceeds, I think this is a 5 volt Zener, so the moment it exceeds 5 volts, it clamps it at 5 volts. So clamp it here at 5 volts. This is the output at this point. Maybe I'll change colors to make that clear. So output at this node right above the Zener, the cathode side of the Zener, is this voltage follows along like normal, but now I hit 5 volts and I'm going to clamp it at 5 volts. And then I'm going to get this part back again. Little issue here about what happens when it goes negative. Oh, there's a ground there, so I'm actually offset because I have a resistor on both sides. So it doesn't, I'm shifted, but so ground is now down here. 0 volts is down here. So when I get above 5 volts, I clamp it, I go down and around, and I come up here again, and I clamp it, and I go down and around, and then etc. And then I go through the inverter. Actually, I should simulate this and show it for you. So inverter says, and it's a Schmidt one, so I don't have to worry about this messiness right in here. And Schmidt says, invert. So I have high, 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 low, high, 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 or low, and then I'm back to being a high, and now I'm back to a low, and then I'm back to a high, and I'm back to a low. So anyway, this ends up being now 60 pulses per second. They're pulses, it's no longer a sine wave. This was running at 60 hertz, and now we have 60 pulses per second. But we want to get 1 pulse per second ultimately to drive this circuit. So what we do now is we use a divide by 10 section. So it's a decade counter, and we can get the output frequency to divide by 10, followed by another counter, which is a divide by 6 section. So we end up having divide by 60. In the end, we have 1 pulse. Time goes by, another pulse, and we end up having 1 pulse per second ultimately. I think this is kind of a cool example because you start from the 60 hertz of the wall and you get down to having a 1 hertz or 1 pulse per second pulse that you can do timer applications with. And a lot of circuits work that way. They're using the 60 hertz from the wall and doing the dividing it down to get it to a 1, whatever time base is needed. But I will mention that 60 hertz out of the wall is not a perfect 60 hertz, so there could be some error in there. Oh, where's my mouse? There it is. What I have here is something, is you take your 1 pulse per second now, and you need one more counter, and this is one that's going to count those pulses, but when it hits number 13, it's going to reset. So I have one more counter right here, and when I hit number 13, I reset, and when I reset, that reset occurs on the 12th pulse. Yeah, so it's the 12th pulse, or when the number gets to 13, the reset occurs and turns on the LED. So kind of an interesting design. I liked the design. It was kind of neat if you think through it all. Here's another one. It's very similar. The timing is a little bit different. Last example is do a counter that counts from 0 to 999. In this case, we are going to use mod 10 counters because we're always doing things in, or they're also called decade counters. We're always doing things in increments of 10. So you just are going to cascade 3 mod 10 or decade counters together. 1 clock input. The first one gives you the LSB. So this is BCD output right here that you could go to a BCD to 7 segment converter and drive a little LCD 7 segment display if you wanted. And when the most significant bit is a 1, it drives the next one, etc. So you can get your numbers counting up to 999. Oh, I guess there were 2 more designs. I forgot about the 2 more. One's a digital clock with hours, minutes, and seconds, and another one is an egg timer circuit. So let's take a look at those designs too. That's out of your textbook. This would be the clock generator. So if you think about a clock, you have, and in case you can't read it, I may make it bigger. How did I? You have, in a clock, you have a section with hours, which has to go between, it says right here, I don't know if you can read it, 00 to 11. Minutes are 00 to 59, and seconds are also 00 to 59. So how would you implement that in counters? This is a little bit more of a block diagrammy of a figure. And you start with the least significant part, which is your seconds. So this is the least significant, is seconds. And then it has to work upwards from there. So I'm just counting, it looks like I'm counting seconds from here because I'm using this clock generator. So I have 1 pulse per second coming in. You can consider that from the last design if you want. How do you get 1 pulse per second? And it goes into a mod 10 counter, which gives you 0 to 9. and there's also a mod 6 counter because we need 0 to 5. So we need 0 to 5 and 0 to 9. So that it corresponds to the mod 10 counter and a mod 6 counter. When you get to the most significant bit of these counters, you go to a mod 10 counter and a mod 6 counter. Why? Because I have to display up to the numbers 59. So 59 would take a mod 6 counter, or the 5 would take a mod 6 counter, and the 9 would take a mod 10 counter. And then finally you go to the hours, which I have to go between 00 to 11, not 11. So 00 to 11 is 0 to 9 on the least significant part and 0 to 1 on the most significant part. So 0 to 9 on here means that I need a mod 10 counter, and then the most significant, which would be either 0 or 1, would be a mod 2 counter. So the last one was an egg timer. You want something to precisely come up with 3 minutes and then buzz a buzzer. So here's a push button restart that happens, and it shows a 1 pulse per second clock that we already used before because we know how to get 1 pulse per second, which is kind of nice. And we're getting our 1 pulse per second all the way from the 60 hertz that is our wall power. So that's a nice little thing to be able to design timing wise. And that, of course, is depending on our 60 hertz being exactly 60 hertz. But in reality, 60 hertz in the wall is not exactly 60 hertz. So we just want to count up to 3 minutes. So 3 minutes is 360 seconds. Is that the way they did it? Nope. Pause here for a second. So it's not 3 minutes is 60 times 3, which is 180 seconds. So we need to count 180 seconds. So I see mod 6 and mod 10. That does a divide by 6 and a divide by 10, divide by 60. But we're using it to count the pulses, so you count 6 and then count and wait 10 more. So this must give you 6 times 10. This gives you a minute. And then the last one must be to give you the 3 minutes. But I'm honestly actually not seeing the 3 minutes in here. So I'm not quite sure there because it doesn't look like this is the one giving you 3 minutes. So 3 would occur when you hit 4, and then you should reset. So I'll look at that one a little bit more because I don't quite see it happening 3-minute timer there. But anyway, neat examples, I thought, because they were all based on how do you generate timing from the AC, beginning with the 60 hertz coming out of the wall. So I thought that they were pretty neat examples. Next section in your textbook, why it occurs here and not earlier in your textbook, talks about the 7-segment displays that we already had a lab on. So counters have to output BCD, so you probably need a binary to BCD, or you have to get BCD converted to 7-segment display. We already had a lab about these. This is just a review showing how there's little diodes inside of each one. The other review is with the other inputs, so BCD input, 7-segment display output. Lamp test is LT, and ripple blanking input and outputs. So just a little bit of a review in case I think I reprinted it for you, in case you want to look back on it for your lab. Your book has a section on microcontrollers with a really old microcontroller, and then it goes into synchronous counters. So we will look at synchronous counters on Tuesday. I think that you have a lot of material just looking at the ripple counters, and understanding the frequency division and what modulus counters you're using to get the kind of outputs and timing that you're desiring to get. So, okay, go work on labs now. If you don't get the lab done Thursday night, that's okay. We can finish it up on Tuesday, and also any questions about the counters. Okay, bye.